Problems, problems, problems. What to do, what to do. Okay, well, what I should have written here is find A, B, and C without reinventing the wheel. Okay, don't want to do too much calculation. We want to do more thinking. More thinking, less calculation. Well, I suppose that's not fair. We're missing a fact here. A nice fact. Okay, row operations. That's what I mean with this dot, dot, dot here. Okay, what I'm saying is that this matrix, when I do some row operations, elementary row operations, I can arrive here. Back to my fact. Fact, row operations do not change. We'll say dependence relations between the columns. Okay, so what am I saying? I'm saying that if I have a relationship, between the columns here, which I do, you can just look at it, you can see how I can add up these two columns to get that column in a certain way. So what I'm saying is that if I have a relationship between the columns here, then that same relationship is going to hold here. Let's quickly sketch why that might be true. Okay, very briefly, if A is row equivalent to B, so if I can take A, do some operations, arrive at B, then if I think about these systems, AX equals 0, then AX equals B, no, BX equals 0. What? Okay, those two systems are going to have the same solution set. Again, that is saying that if I take an X here that passes this test, then that same X is going to pass this test. But what is A times X? A times X is a linear combination of the columns of A. Okay, so what I have here is it's written as a matrix equation, but you can write it as a vector equation. Okay, you have a linear combination of the columns of A is equal to 0. Okay, so I have a dependence relation between the columns of A, and we're saying that that same dependence relation must hold here. Okay, so that's in a nutshell the proof of this fact. We're going to make use of it right now. We're going to say, again, we're going to say that any relationship that exists between the columns here is also going to exist here. And it's easy to see where the relationship is here. We can see that if I have if I have 3 times that first column plus the 2 times that second column is going to give me the third column. So a relationship between the columns here. Now what my fact is saying is that the same relationship, with 3, 2, you can think of this as a 1 here. And that same relationship, 3, 2, 1, is going to hold between the columns back here. A, B, C. 6, -5, 9. Make sure I didn't screw that up. 0, 3, 3, A, B, C, 1, 2, 3, 3, 2, 1. Okay, so now you can see what I'm trying to do here. I'm going to try to find A, B, and C from here. So what do I get? I get 0 plus 2A is 6. 9 plus 2B is -5. 9 plus 2C is 9. C is 0 from that equation. B is -7 from this equation. Don't check my notes. Am I on the right track? Am I on the right track? I sure hope so. I'm gonna have to go back. Et voila. A is 3. So let's recap here. Oh, something's gone funny. What has gone funny? 2C9, 6, -9. Aha. Typo. -9. -9. C is -9. Just barely caught that one. All right. Recap. I want to find ABC. Okay, you could I mean, there probably is a way to row reduce this and then just force it equal to this one and try to figure out A, B, and C. Good luck. Better to use this fact. Okay, row operations don't change. Sorry. The relationships between the columns don't change when I row reduce. That's the fact. So my relationship that I found between these columns is also going to hold for these columns. And from that, I was able to quickly find A, B, and C.